Okay, so continuing on with thermodynamics, the other thing we're doing is calculating the amount of energy required for a phase change. So a phase change is something like uh, going from solid to liquid, melting, or going from liquid to gas, which is evaporation, or going backwards from a gas to a liquid or a liquid to solid. So freezing, melting, condensation, evaporation, those are all phase changes. And we want to calculate the amount of energy required for those phase changes. Now, why would we need to do that or want to do that? What makes it different than calculating the change in temperature as we did earlier? Well, the interesting thing is that when you go through a phase change like melting or evaporation, the temperature doesn't actually change. So let's say this is the temperature here going up, and this is energy going this way. Um, this is where you have ice. This is where you have liquid. This is where you have gas. And these plateaus right here, these flat areas, is actually where it's melting or freezing, and where it's boiling or condensing. So how you read this graph is that if you have ice, you increase the temperature, you put energy into it, the temperature of the ice will raise until it gets to its melting point, at which point you continue to put energy into it and it starts melting. It starts melting, but all the energy goes into melting the ice, and the temperature doesn't actually change. Same thing when you get up here, you're raising the temperature of the liquid as you put more energy into it, but once it gets to its boiling point, all the energy that goes into it goes into boiling that water away, and the temperature doesn't increase. So you put a pot of water on a stove and you boil it, you can leave that pot on that stove forever and it will never go past 100 degrees C, because once it hits 100 degrees C, it'll just start boiling away, and all the energy you put into it will go into boiling the water away instead of raising its temperature. So it requires a different formula to calculate the amount of energy to do something like melt ice or freeze ice or boil water. And the formula we use is Q, again for the amount of energy, Q N delta H. So N is going to be the amount of your sample, and the delta H is going to be the heat of fusion or vaporization, and that's just a fancy way of saying the amount of energy you require to melt or freeze something or evaporate or condense a certain substance. And this is going to be this number here, the heat of fusion or vaporization, is going to be a constant. It's going to be different for each substance, but always the same for that substance, kind of like the specific heat. So I can do let's do an example problem here from the study guide. Let's do number 3 here. How much heat is needed to melt 45 grams of ice at 0 degrees C? Okay, so it's already at 0 degrees C, which is the freezing point and also the melting point of ice. So we don't have to worry about changing the temperature. All we need to worry about is putting energy in to melt that 45 grams of ice. So again, during a phase change, the temperature doesn't change. All the energy goes into doing the melting in this case. So how do we figure out the amount of energy? So Q equals N delta H. So N is going to be our amount. In this case, it's going to be in grams. So it's going to be 45 grams of ice. And what's our delta H? The heat of fusion of water is given to us right here. 334 joules per gram. That means for ice, it's going to take 335 joules to melt each gram of ice. And so the formula is simple enough. If that's what it takes per gram, well, you multiply the total amount of grams you have. So 45 times 334, let me get my calculator, times 334 equals 15,030. 15,030 what? Well, the grams cancel out. You end up with 15,030 joules. That's how much energy it takes to melt 45 grams of ice.